Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about high voltage transmission lines. So let's dive right into it. Well, why do we need high voltage transmission line? Well, reality is very simple. Power generation and consumption can be spread apart. For example, this is Indian grids and you can see there are sections. Now here's deal, does not mean everything that is in blue can only supply to everything that is in blue. There could cross transmission can happen, and distance between these things could start at 100 kilometer and can easily extend to lots of kilometers, as in like 100 to 800 to 900 kilometers, like really long. And in case of USA, some could be ludicrously long. In case of China, there is one like that is 1200 kilometer. So it's very far apart. And here's the deal, why do we need exactly high voltage? Well, there is a trick in power equation, that is basically the amount of energy that you are transmitting has loss. That loss is like I square R. Now basically that limits how much power you can do. Here's the deal, you may think, what about we use thicker cable? That will reduce the R. Now that's it, all you are doing is reducing it, so that's good. But what if you can reduce the current, as in like the I, powers by square, meaning if you reduce it by a factor of 10, the total loss will go down by a factor of 100, meaning that's far more preferable to reduce your current rather than reducing your resistance. While ideally you would try to reduce both of them, but unless you are superconductor, you really can't do much about resistance, again due to cost and physical size limitations. So the best option you have is current reduction. So that's why we really work our ass off to reduce current as much as possible by increasing voltage as much as possible. And we need to connect it all, because here's real, if you have all this grid connected, there is a scenario where if you have power fault, flaws, lack of coal, these sort of things does happen. Like you can have tragedies, you can have earthquake, you can have malfunction, things of this nature does happen. Right now in current scenarios, like if something bad happens here, it can literally not affect anything else. But here's it also works vice versa, meaning if this area is working awesome, no problem, everything is working, every plant is fine, and we had coal shortage here, we can't transfer electricity here. Like literally there could be power plant, you're like, okay, those power plant may be operating at peak capacity, that is true, but what about at night? So if power can be transmitted, those power plants will make more money, and again you can stabilize the national grid, which is far higher priority than you realize. So connecting all of these is a desire. And again, at the early days, we only had like each state had its own system. Slowly we consolidate, and over time we have to consolidate everything if we have to integrate renewables into it. Right now there are some solar farm here, some solar farm here, some wind farm here. Like we have to consolidate all of this. There is no other option, like we have to do it. So that's why we need high power transmission lines or high voltage transmission line. Now there are certain details to this puppy. One of the primary detail is that supply and demand must remain in sync, as close to as possible. Now because if it does not, the best case scenario is a grid goes down. Now grid going down could reach a point which you call black start. Black start simply means you have to restart the grid. Only some power plant, you could have 1000 power plants, but only some power plants could be big enough, robust enough that can endure black start. Majority of power plants never go down, like literally they do not go down, unless, as in like unplanned schedule system. So if majority of the power section goes down, it literally has a cascade failure. Why? Because entirety of the grid is what we call inertia coupled, meaning how does a power plant produce exactly the amount of power that you need when you add the load? For example, let's say a steel furnace turns on a giant induction furnace that's consuming 10 megawatt. Here's steel. How the heck that 10 megawatt was conveyed to power plant? Hey, can you increase 10 megawatt? They don't. What they do is use coupling. Basically, everything is coupled. The power that you are consuming is coupled to the power line. That power line is coupling power from transformer to transformer to transformer to the generator. Generator is being mechanically coupled through magnetic fields. So there is actual coupling there. What does that mean? That means there is spinning mass, as in like the rotor of the generator is rotating. That's massive. Then you have shaft. That could be idiotically heavy. Then you have turbine. That could be really, really heavy. All that mass is spinning. That inherently means it has inertia. Inertia buffers it. Meaning, if your generator is producing 500 megawatt, let's say its maximum rated capacity is 600, it's operating at normal range of 500, everything is awesome. But you turn on the load of 10 megawatt extra. 500 was doing good, now you are demanding, the demand went up by the supply by 10 megawatt. What will happen? Now there are sensors that on generator shaft that is looking at the RPM. Let's say RPM is 1500 RPM. And that RPM is directly corresponds to the hertz in the grid, as in like 50 hertz, 60 hertz. Now, when they are looking at the hertz, they're like, everything is fine, everything is tight, everything is good. And then they're like, wait a minute, why the heck hertz went down from 50 to 49.99? Okay, computer now would be alert. Okay, something's off. Then they will 49.8. At that point in time, they know there is a lot of inertial loading on that turbine. They will open up the steam valve, spin will start to spin up, and it goes in other way also. For example, if somebody is like, draining a lot of power and then shuts it down. For example, cricket stadium in India consumes GG amounts of power. They shut it down, all the turbines will start to spin up. Again, because of the mass, because of the inertia, there is a lag there. It won't happen. It will be like, now this time is more than enough for computer to like, hey, throttle the steam valves, tone it down as much as possible. So that's why we need to have this sort of coupling. We need to desire, it's a desirable thing. That's how our grids are stable, because if only one generator was coupled this way, it's gonna go down as quickly as possible, because the moment you had even a minor spike, there is a chance it may not be able to absorb as much impact as possible, and then circuit breaker will trip. Now, if you couple hundreds of generators over a nation, then it's robust enough. Even a very powerful spike can barely do anything to it, because so much inertia is magnetically coupled there. It's like, bro, we got this. So you have to manage it. Supply and demand must remain very close to each other. They are almost chasing each other. It's like, so it has to be done. Now, no line is ever at 100%. This is one critical aspect, because everybody who started to connect all these grids realized very early on that you could require a scenario where you have to reroute power. There could be hundreds of reasons for rerouting power, or like, diverting things. For example, let's say you have a generator maintenance shutdown, meaning you have to shut down the generator for maintenance. Okay, that means the power deficit, because again, demand is not changing, only the supply is changing. Somebody else has to supply it. Somebody else have to crank their puppy up to 100%. Now, here's the deal. What's the point of pumping 100% of your power if the grid line is already saturated? So all grid lines, basically interconnections, they are tried their best to be as low as possible, meaning 50% to 80% utilization. They will never try to like max this puppy up. And again, it strains a lot of electrical load onto the grid, meaning the cables heat up too much. And if they heat up too much, there are risk of sagging, and then sagging too close to it increases loss, which increases more power draw. Feedback loop can damage the system. So no line is ever at 100%, and that 100% is only achieved if you have reroutes, if you have fault, meaning if this section is unsaturated, all the energy that is now being overproduced has to be channeled through this line. This line will consume its spare capacity, and it has to be done overall the grid. Only then we can have like, okay, one line down, okay, reroute power everywhere else. So it does work at this point in time. Now, higher the voltage means higher strain. You may have intention like, hey, if we can reduce the ampere by, let's say, 10x, we save by 100x. Awesome. What if we drop it by even 100x? Let's go voltage YOLO. But here's the deal. Highest voltage we have tried is around 1200 kV. There are some HVDC links, there are some AC links, but generally nobody wants to do that, simply because higher the voltage means higher strain on every insulator in the chain. Now, even these insulators, they have a requirement. They cannot be just like put GG amounts of voltage. If you increase the voltage without changing the insulator, those insulators will become conductors. And where is the biggest strain on this? Transformers. Each transformer have windings. Those windings have to be as tight as possible. Consequence, they do not have enough space for insulating materials. So insulation is really not magical there. It's like that's the upper limit. Then you also have switchyard. Again, switchyard has to deal with those power. Like they have to have basically switch gear that can disconnect it, circuit breaker that can disconnect it instantly. All those things require things that can withstand that kind of voltage. And higher the voltage, higher the strain on the equipment. So you cannot just like, let's go GG in the higher voltage. Like there is a cost association. You want to be like as conservative as possible. Then what should you do? Use AC or DC? Short term, AC, we use AC simply because it's cheaper. DC is better, but AC is cheaper. So that's why we use it. For example, but again, in some scenario, you have to use DC. For example, if the distance is long, or distance is to go through sea water, for example, offshore wind farm, the moment they cross 80 kilometers, they have to do DC conversion, meaning high voltage AC will become into high voltage DC, HVDC, and then they have to transmit, because AC has idiotically high capacitance loss. And if you are like Europe and you are like trying to connect all the nations, and many of the nations have to be jumped through sea, these things have to be high voltage DC. And high voltage DC also has this benefit that you can do monopole, meaning it's just one pole, done, go home. Like in AC you can have 3 poles, but here 1 pole is enough. So you have to choose. So AC cheaper, DC better. That's the whole point. You have to analyze the cost and the need. If your distance is very long, you cannot use AC. For example, if you are longer than 80 kilometers undersea, you have to use DC. You do not have the option of AC. So that's up to your choice. Submarine cables, these things have to use that. Underground cables are also expensive. You can bury these sort of AC lines, but they will not last long, because again, when you are hanging them up, the ground is acting as a certain part of the capacitor. That's what we call capacitance loss. Now, if you bury it, it's literally surrounded by everything that is acting like a capacitor. What is a capacitor? You have a plate, another plate, and an insulator in between. What will happen if you literally take a conductor, bury it underground? Of course, you will insulate it, and then what is outside of the insulator? Another part. Now again, it will not act as a dead shot. It will not act as a giant capacitor. Over a long distance, it will act as a giant capacitor, which we call capacitor. That's why, like, for long distance, you cannot transmit AC powers, as in like hundreds of kilometers. The moment you are like 100, 300, people say generally at 300 kilometers, it starts to make more sense to use DC. And if you are going underwater, 80 kilometers is the dead limit. And if you are like China, you want to 3 gorgeous 12 gigawatt power transmission, you have to use DC. You can't transmit it through AC. So these are the details that you have to work out before you start your plan. Then we come to the cable aspect of it, like the actual puppy that is carrying the main power. Now, your first common sense is like more cable. Fatter the cable, GG the power. Yes, it does not work with AC simply because if you take this cable and you cut it, cross section, how much power do you think is carried by this? If you are thinking normal terms, you will think, hey, whole conductor would be used. Here's deal. That would be true if it's DC. In AC, that will not be true. Current will only through the outer conductors. Why? Skin effect, meaning this puppy is inherently acting as a transformer in itself, like a magnetic thing, eddy current loss sort of scenario. So the core is always unused, meaning it's so unused that people have literally started to, like, first they used to make copper cables. It was very expensive but not that much better than aluminum, so aluminum won out. Then they're like, what if we replace the core from aluminum to steel for higher tensile strength? They're like, dude, that works awesome. Somebody's like, what if we take aluminum and mold it into a much tighter tolerance, much better shape for higher skin efficiency, and remove the core from steel to basically carbon fibers? That's the current cable nowadays. Benefit of carbon fiber is that you can span between your poles can be much longer, like 10 to 30% longer, meaning over a distance of, let's say, 100 kilometer, you will save the number of poles you need. So skin effect makes it like you cannot have like GG cable. You have to have like a very thin cable, as thin as possible and as many as possible. So core used is for strength. That's why the core is, that's why it's not hollow. It's like inherently much more beneficial to have like steel cable there or carbon fiber there. And sometimes you will notice in substation they have hollow pipes. That's the reason. If you have a hollow pipe, it inherently acts like a double skin, like from inside out and outside in. So that's a really efficient use, but you can't have hollow cables. So fundamentally they are like, best compromise is just like have few of this. Now, how do you transmit megawatts of power? This can barely transmit enough power for one small block. If you really want to transmit power for like a nation or a state, this is not enough. You have to have multiple of this. So we call bundle conductors, basically like this. Like China is showing off to the world, like they have like 1200 kV, like the longest, highest span. Now, if you're seeing all of this is in one phase, and that's the easiest way to figure out the oomph of the transmission line. If you see a transmission like a single cable per phase, that's a basic baby cable. Now, if you see double conductors, that's good. If you see triple, okay, 4, now we are talking. 5, you will generally not see. At that point in time, you will jump to 6, and it's like, yeah, 6 means some serious amount of power is going through. 8, like this, is really large amount of power is going through. So that's why we use bundle conductors. That's the only way to transmit very large amounts of AC current without losing majority of your conductor mass to skin effect. So fundamentally, we have to use bundle control. It improves efficiency. Now, it also has another benefit. Even if you are transmitting DC, it does reduce your lower corona, because if you spread this puppy out, they act like a giant conductor. Like inherently, they are a giant conductor. So if you have all of them, the basically gradient, the highest voltage potential and zero potential of air, it will be very sharp. The sharper it is, the more corona it will create. You want it to be gentle. You want to be like, hey, spread out, chillax, take some chill pill. Spreading them out this much where a person can fit inside reduces the voltage drop, as in like a voltage loss from corona discharge very low. That means much more efficient transmission. That's why even if you can transmit into a fat cable, you will not, simply because DC will also suffer from corona discharge. And then we have to come to another aspect. Every conductor heats up, especially in summer, it heats up. Now, it has to cool itself. How the heck it will cool itself? Again, if it's spaced out this far apart, it has enough airflow where it can chill itself down. If you used one thick one, the core literally could reach a point of melting. So that's why we use bundle conductors. Then we have the side effect of like, if these things are so big, so far apart, they are getting, love made by wind. What do? You add dampers, this sort of dumbbells that you see. Now, these things are what we classify as tune mass dampers. Basically, they are fine-tuned. Basically, for the length, they are fine-tuned for it, for the mass, the resonance, and all that. Like there will be studies conducted, then this puppy will be attached. This will absorb all of the energy. Again, it will not eliminate it, but it will reduce the damage done to this puppy. So the cables can last like literally 70 to 80 years. This is just on the cable side. let's we come to the second part, pole. Basically, how do you stand this puppy up? Higher the voltage, larger the pole. This is another aspect of it. You may be like, hey, let's just go to 800 kV. Here's the deal. Do you have the money to pay for the poles? Because pole height is directly proportional to the voltage, because again, you want these things to be as far apart from ground as possible. Again, because the lower leads are literally acting like a one side of the capacitor plate. You want to be as high as possible. That increases cost. And you can easily guess, like there are some engineers who are so good, like they look at it, they look at the height and it's like, yeah, that's 135, that's 230, that's 500 kV. Oh, that's 1200. Like again, I'm reasonably sure most of you can just spot 1200 kV because it would be so tall. So you have to figure that part out. Clearance from the ground. And another aspect is, you may think, okay, just I have to make it tall. Not really. You have to make it large also. Simply because the cable clearance between phase lines has also have to go. Basically, think of this: the conductor, there is a sphere around it. Not sphere, cylinder around it, and that's the air insulator that you are providing. So it cannot intersect, basically go next to the another phase line. So these two things seriously limit how much high voltage you can use. Then we come to also other aspect, the brutal aspect is like, it has to be cheap because you're gonna need a lot of it. Even if you're spanning only 100 kilometer, you're gonna spend a lot of money into that. Because if your pole is like even a little bit more expensive, it's like, yeah, by 100 kilometers, like, dude, how, like, it's like ludicrously expensive. So you want to be as wise as possible. Then we come to another aspect. Which pole do you choose? Do you choose lattice type like a normal mobile tower, or do you choose monopole, this sort of modern construction? Lattice tower is cheaper, monopole construction are far quicker, and they rust less. That is another interesting aspect. They rust very less because the surface area, while it does look large surface area, it is nothing compared to like, small bars. And there is side effect of it specifically in like some parts of like poor parts of Africa is like countries wanted to install this, but people started to come there and use angle grinders, battery power angle grinders, cut the metal, start to sell in scrap yards. Like literally, I'm not joking, this happened. It's like a tragedy of poverty, but that was a serious fault for government. What they had to do is go like take much larger loan for this sort of pylon system, because again, pylons are a bit harder to steal, and they knew that somebody will try to instill the bolts, so they've bolted down, tested everything, then they put concrete on top of the bolts also. So there are some benefits of going to basically monopole. And again, monopoles is far more preferable compared to lattice system. Again, personal preference, but they do take less footprint and land cost money. So that's a desirable thing. Now let's just come to the normal towers. Then there are special tower. For example, special towers are generally used in every corner, meaning if your conductor is like holding like this, awesome, GG, super cheap. The moment you have to do hold conductors like this, meaning conductor is coming here and then it's bending, it puts extra strain on the system. The tower that are at the corner, you will find them, they are bit beefier. You can easily notice it. Dude, I think this is lattice towers. You can literally say, hey, I think this is a bit beefier. That's the reason at corner, because again, the loading is not just gravitational loading, it's like lateral loading also. So they have to be like, I got this. So that increases your cost. That's why you want it as straight line as possible, otherwise cost. And then we have transposition. This is an issue with DC AC system. You have to have this sort of pole. Now where will you have this sort of pole? You will take the distance, whatever the distance may be, 300 kilometer, 100 kilometer, whatever the, take that distance, x, divide by 3. So let's say the link is 100 kilometers long. Every 33 kilometer you will find this. Basically what it's doing is intermixing the phases. Basically if A phase was on top, B was here, C was here, they're like, hey, B will go up, A will come down, C will move here. And they have to do it 3 times, so they balance everything out. Otherwise, one of the phase could literally go out of whack. Like again, AC does have issues. So again, every long transmission will have this, and I guarantee you will notice them and it's like, what the hell was that? Which call it transposition. These are the 2 things that you have to pay for also. And ground must be cleared from trees. Even though ground, it has the air cone, that is the insulator part, a tree may not affect it directly, but in rain it will affect it. So that's why you have a lot of shots in rain. So the area below the tree line, I'm saying basically high voltage line, has to be cleared of long trees. So we come to the final, Thanos. Now Thanos is very wise in this regard. Perfectly balanced as everything should be. Because reality is there is no magic solution. You may be like, hey, why don't we use HVDC for everything? Would you pay for it? At the end of the day, you have to find something that works for you. For example, they were using, in some places in Africa, they have to use HVDC because they were transmitting power for such a long distance, they had to use it. They had to bear the cost of it. In some scenarios, they had to bear the cost of monopoles because otherwise people will just steal it. Yeah, that's a thing. That freaks me out. That's a thing. But again, they had to adapt to the situation. So there is no magic solution. it works, that just works for every scenario. You have to be wise and you have to balance things out. And we want the best, because every time there is a tornado, every time there's a minor car accident or tree falling, everyone's like, why don't we bury the power line underground? We can do that. We can do that. Physics does allow to do that. It's just that, would you pay for it? Some governments did the mathematics on it. Like, actually, okay, here's the contract, just figure out the mathematics of it. The reality was, every power bill will double, just double. How much energy you are paying for, basically X amount of money you are paying per unit, that X will become 2X. Everybody's like, no, 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 no. Again, that's the whole point. That's why we don't bury it. It's expensive. And not to mention, does not even last longer. Again, it's a capacitor, so it inherently wears down much quicker. So a same conductor slung in the air away from everything can last 70 to 80 years. Things that are buried, good luck, 30 years. So HVDC is much better than HVAC, but converter station, because again, their generators are still AC. You step up the voltage to high voltage, still AC, and then once you have that high voltage output, then you make it into AC. Now that should freak you out. It's like, do you really want to make love to ludicrously high voltage AC directly? You're interacting with it. You're not just like, okay, I take it and throw it away. No, no, I'm going to interact with it, and I'm going to chop this puppy up, and I'm going to make it into DC. Yeah, no, that's very expensive. That's why converter stations are very, very expensive. But again, if some scenarios you have to use it, you don't have any other option. These are like a submerged cutaway of a submarine cable, high voltage DC. Again, thankfully, because it's DC, it can utilize the core. Consequence, you see this insulation, this thickness will go YOLO if you increase the voltage. So they have to balance it out. They may be like, hey, what if we just put, instead of sending 500, we send 800. This will become longer. Now imagine this cable is like, let's say 150 kilometers long. Would you pay for it? So you have to figure out. Underground is robust against tornadoes and all that jazz, falling trees, car accidents, awesome, GG. But here's it, they are really weak against flood, simply because cables are come from factories like properly made, because otherwise you cannot guarantee this insulation. So they have a cable gutter, basically cable vault sort of scenario. So let's say a cable is 2 kilometers long. Every 2 kilometers there will be a cable vault. How do you see which part of the link broke in a earthquake, in a flood? You don't. You have to study every single cable vault. Is like, hey, I think it's working from here to here, or put sensors throughout the link. Again, HVDC does have a fiber intermediate, because the cable is so expensive. It's like, it would be much wiser to invest extra cost just to have fiber throughout the line, so you can figure out where the cable break happened. So again, balancing. If you are in a scenario where like you rarely get snowstorm, but you get a lot of flooding like India, you're like, dude, put it on top of ground. In some scenarios, you will be like, hey, if let's say Delhi is there, you have already a lot of high voltage lines going there. You're like, hey, we already have a lot of over sky. How about we put some underground? And that gives you buffer. Like in some scenarios, let's say wind topples over your, above ground, underground will take up the load. If flooding takes over your underground system, above ground will take your load. So you have to balance things out. And lifespan is also considered, because these things, customer will not pay for it. Again, there's a small chunk there, but it's very small. Customer does not like to pay for transmission line. So you have to balance it out. Lifespan directly means how comfortable you are. As in, like, if lifespan, somebody says, sir, these poles are amazing, this conductors are amazing, this will last for 70 years, no questions asked. You're like, shut up and take my money. And somebody is like, sir, this is underground, buried, everything is awesome, you don't have to worry about winter. Again, for Canadian people, it's like, shut up and take my money. It's a very big deal for them. For Indian people, it's like, dude, we have so much flooding, it will be a hassle, just lay it above ground. So lifespan is a very serious consideration that goes into the cost of it. And multiple redundant paths, that's the key aim. And that's what every country is doing. That's what even Ukraine is doing. It's like trying to have as many parallel routes as possible. So each route is very underloaded. And when you have a scenario where like somebody booms your substation, you can just like reroute power. So multiple redundant path is a must for stable grid. So that will the only way you can have like 24/7 electricity without any issue. And balance is the key. At the end of the day, Thanos wins. Balance is the key. So this was my presentation on high voltage transmission line. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. Press it twice to show me extra disappointment. Please leave a comment, because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.